about what we are doing here in statistics. If we say, what is the purpose of statistics? Which was already mentioned in the previous information that we had. What can you tell me? What's the purpose of statistics? That's correct, data-driven decisions. And what does that mean?
To expect.
I want to know what to expect.
Trends.
And that includes trends. And what else? Yes, but I'm looking for something more specific.
Guess that less than 5% chance of happening, more than 5% chance of happening. Unusual events.
Okay, there are a few things there that are correct, and so we'll try to distill them. So when we say what to expect, if something has a less than 5% chance of happening, then we say basically no. We think that's not going to happen. And then what would qualify as a yes?
More than 95%.
Right? More than 95%. And you might have said that, but I just didn't get it. So then the concept that we work with is if an unusual event occurs, that might be an indication that's going to give us the information that we want. So if we say something like, I do a survey of students at Western, and I find out that 70% of them have watched English soccer, okay? And then I might ask the question, am I surprised by that? Would that be an unusual thing to happen? And if I have some idea of what other people say in terms of that percentage, then I might be able to say it would be unusual for that to happen. So then I might say Western students have a higher percent, that they're more interested in English soccer than the rest of the population. If I can establish that it's an unusual event, then I can say this group is different from some other group. And then that extends into various kinds of data set that I might have. If I have a data set and I say I want to know the distribution of the data, I want to know what that data looks like. And then once I establish what it looks like, then I can get an idea of the unusual values for the data, things that happen less than 5% of the time. Now, just because I take a sample, we already talked about this, doesn't mean I can necessarily believe that or think it's true, but it's possible that that can be an indication of rare events. And we'll talk more about that as we go through here. But what we need to do then is to establish the kinds of information that are, if you want to say, kind of geometric interpretations that make sense to us. How can we understand different aspects of data based on the graphing that we're able to do? And so what we do with this in a situation is that we have to establish different types of graph that are going to help us to give us different kinds of information. So there are three basic geometries that we work with, and then we're going to add more as we go. But the types of graph that we have a line graph, a bar graph, and a circle graph. And you know, if you've if you've seen or if you Google line graph and you see what it looks like, and you can tell what's happening, or even in the PowerPoint it talks about this. If I have a graph which is using a line, what is it about the geometry of the line that gives me my information?
Increase or decrease?
Okay, so a line is going to have direction.
Yes.
And so when I'm looking at a line which has direction, then that means I'm looking for the change that's happening in some number. And specifically, this is going to be used for change over time. Now, as it turns out, textbooks are not consistent with this. And I can see sometimes how this might be different. But if we say that we have a number and it's for like all the years since 2010, and we have a list of numbers and we have a list of years, normally we're going to use a line graph for that because we want to see what's going up and down and how does that kind of thing work. Now, in that kind of a situation, I want to give you an example here. If we talk about just say the Dow Jones Industrial Average. This is what the Dow Jones Industrial Average looks like for today. Notice that when we do this graph, we don't have to go all the way down to 0 on the vertical scale. We are actually kind of zooming in on this graph in order to see the actual changes that are happening. Today, it's only been between 23,750 and about 2,400. So there's not really a lot of change. It's just kind of bouncing around. If we were to do it like for the past year, then we would have a different range of possibilities. It went all the way down to 22,000 not too long ago, but it's recovered up to 24,000 right now. It has been as high as 26,000 during this past year. But it doesn't seem like there's a real trend, either up or down necessarily. There was an up season and certainly a down, maybe surprise here, and people were not expecting this to go down, but it's come back up here. Most people aren't panicky right now about the stock market and what it's doing. But again, there's no real reason for us to go all the way down to 0 in this situation. We just want to see the changes. And of course, we can identify the trends. If we go for more time, if we go for 5 years, then we can see there's a definite up. Started in 2016, about 15,000, and then it's been up to 25,000, and then kind of went down significantly right here just recently. If you were going to buy something that cost $15 and then it went up to $25, would you consider that substantial? Yeah, that's what happens to the stock market here over the past 12 months. These are the prices of these items, right? From 15 to 25. So that's really a big deal. And when you say there's trillions of dollars out there that are being invested and people getting huge returns like this, then you say it's kind of a big deal when they don't get those returns and those things go away. But, you know, and I'm not an economist. If you talk to David Reed about it, maybe he can tell you all the ins and outs of the stock market. But the basic idea is that people who own businesses, and especially people who are involved in corporations, management and so on, they get benefit from this, but so do people who are retired because they invest their money and then they get something because of that investment. So yeah, anyway, you can see the change and that's how it happens. Now, when we do a bar graph is different because a bar graph is using rectangles. And in the bar graph, we're comparing the size of the rectangle. So when you look at the size of the rectangle, you want to be able to say, this one's bigger than that one. And so you do have to have a 0 on the vertical scale and then an evenly spaced scale going up to know exactly what that is. Because let's say we're talking about Wisconsin versus Illinois or something like that, where we would have this like this and this like that. We would want to be able to say these rectangles are actually representing the number of people or drivers or whatever in each of these categories. So we have to have 0 at the bottom, and we have to have an evenly spaced scale for this to work. What we have down here on the bottom, these are just basically categories. They could be any kind of category that you want, but they're just basically different sets of data, different amounts of people or whatever, and you're just comparing how many people are in the different categories. Now that's different from a circle graph. Even though they are related, what is the thing that you get from a circle graph that you would not get from a bar graph? What is the geometry of a circle? What is that telling you?
You get the whole picture.
Okay.
Everything that's inside of it.
Right. So then with the circle, you have parts of a total. So you have to kind of be careful. You can't make a circle graph unless the things that you have represent everything. Okay? So like, and these are very common in business situations where people will say, this is our entire sales for this year, and it's broken up into these categories. And so then generally we're looking at percent when you do that. Now, as it turns out, it's not really necessary for you in this class to be really good at making circle graphs, but it's not really that hard either. Once you understand the idea of percent, that you would have just 25% over to the right, 50% at the bottom, 75% here, and this would be 0 and 100%. So you don't have to necessarily think about it in terms of degrees or protractors or anything, but just the general idea of how big the different parts of the circle are, or the pieces of the pie, right? Pie chart. Yeah, it never really became pizza. It was just pie itself. Rather, there's other things you could cut into pieces like that. No. So this is a pie chart or a circle graph, and it's dealing with the parts of something you have as a total. Now, when we then ask the question, how are these things that we have here, how are they related to that up there? What to expect, the trends that we have? That's not an easy question to answer. Simply because you have things that are bouncing around or moving one direction or another, you don't necessarily know that that's what they're going to do in the future. So you can find a trend by doing a line graph, but then you don't necessarily know if the future is going to be exactly the same or it's going to follow the same pattern or anything like that. So, I mean, there's an entire branch of statistics that's devoted to analyzing trends using line graphs. Bar graphs, though, and circle graphs, you can find things that are less than 5%. And you would say, if it's less than 5% chance, then that would be an unusual thing to happen. And if it's more than 5%, okay. But we, in order to make this happen for a data set, we're going to have to understand something else regarding how data can be organized. So if you are able to get to your textbook from where you are, and if you go then, if you're in the website here, then if you go to the general MyLab statistics page, it does have e-text as an option, and you can go there so you wouldn't have to have a physical textbook with you, but either way is fine. So if we go to page 76 in the textbook here, then what you see at the bottom of that page is the number of people who arrive at Wendy's. And this would be a relatively common thing for people to say, you know, what are we looking at here? I'm just trying to figure out how many people are coming to Wendy's for lunch. And we just pick 15-minute intervals, and we have a collection of numbers. Now, when you look at this collection of numbers, what would you say? How would you organize this in a sense of saying, can you, by looking at table 8 right here, can you pretty much know what's happening just by looking at table 8? Is there anything that this data set tells you? I am the manager of Wendy's and it's lunchtime. What can I expect to happen? Do I get ideas from this data set?
If you, like, when you can see how many people come in at what time.
Okay.
Usually.
What would you plan for based on what you see right here? You're not going to get 100 people. Are you going to have a lot of times when it's empty?
Yeah. A few times.
I don't see any zeros in here. So,
Between 2 and 11 people,
okay, so we've got between 2 and 11.
probably 6.
6 looks kind of common here. Okay. Well, it would be nice if we had a better way to organize this. And thankfully we do. So we go to the next page on page 77, and we have what's called a frequency distribution. A frequency distribution then is how we can take a data set and we can say, how can I have a better understanding of the behavior of the data? I guess I need my eraser. Don't I? So when I'm organizing my data, one way to think about what to expect here is to use this as a tool, a frequency distribution. The frequency distribution is a way for me to, in a sense, think about the behavior of the numbers. Where are they and what are they doing? Just like if I were trying to figure out what does the cardinal do in the springtime, I would need to find a bunch of cardinals and watch them for a while. So I'm looking at my data and I'm saying, how does it behave? And we see that the 6 is pretty high, but it does go all the way from 2 to 11. And so then frequency, what we're talking about here is how frequent a data value might be. So there are 11 data values of 6. So this is the number of measurements that I made. There were 11 6s. It's really important to understand that the actual measurement is over here. This is the measurement. The frequency is how many measurements I have. So when I do this then, the relative frequency is a really important measurement. because my relative frequency is giving me my percent, in a sense, of how often something happens. So once I establish that I have a data set and I'm looking at the percentages or the relative frequencies, now I can maybe identify unusual events. Would I be surprised if I had 11 people in the restaurant?
Yes.
Why?
It's only 2.5%.
So it's just 2.5%. Would I be surprised to just have one person?
Yes.
Okay. So especially when I look at a data set, it's pretty common that I would consider the top end or the small end and the large end of the numbers to say, where would those unusual values happen? So if I'm the manager of Wendy's, I need to be thinking about how my staff is set up, how the seating is in the restaurant. I want to be able to accommodate mostly between 2 and maybe 9 or 10. But I don't have to have a meeting room for 20 people because it's probably not going to happen. Unless I'd go out and try to make it happen, which I could, but probably not going to happen. So I need to be aware of the behavior of the data and then respond to that in making my decisions. Now, when we work on this, notice that every number has a separate entry here. The number of 6s, the number of 7s, and so on. That's not always the way that we set this up. It can be useful, but it's not the only way. We'll come back to that idea in just a minute. But based on this thing, which we call the relative frequency, then that creates a graph, which we call the histogram. The histogram, which comes from the frequency distribution, then looks like this on page 78. Is it true that people think in a different way when they're looking at a graph compared to looking at numbers?
Probably.
Yeah. It's a different way to look at something, different perspective. So when we have a frequency distribution, that's something, but if we graph it, then that engages a different part of our understanding, and sometimes we can figure things out better if we have a graph and we look at it. Hopefully it's clear by looking at it here. The 6 is the big thing that's in the middle, but there is kind of a spread here around the number 6. So that we definitely would not say it's always going to be 6 in the restaurant. It could be anywhere in this range. Why is there a big thing of 2s?
Date night.
Date night?
Or just lunch buddies.
Or lunch buddies? Generally speaking, when people say, hey, let's go to lunch, they ask one other person. It's usually the easiest way to do it, right? If you say, hey, let's all go to lunch, oh, that's complicated. So maybe if you just get one person going. So it's kind of common for that to happen. And if you've been to a Wendy's or a McDonald's or someplace like that, what do you see? Tables for 2. They have little places where you can just have 2 people because they know that happens. And so they arrange their architecture so that they have those kinds of things. More efficient maybe than having a big table for 4. You can get more groups in that way, right? So yeah, they think about this stuff. Clearly, they make it happen. Now, like I said, that's not the only way that these things happen when we're making a frequency distribution. We can also have a grouped frequency distribution. With a grouped frequency distribution, it's going to have these 3 characteristics. We're going to have evenly spaced groups. there's going to be no overlap. And it's nice to have about 6 groups. So if we have a set of data and we say, I want to know what that data set looks like, it's nice for us to have like 6 things, because then we can kind of get an idea just by looking at it. It's usually easier than if we had 100 or just 4, okay? 6 is usually a good number to have. Here we've got 11, and it works pretty well, okay? So this 6 is not an exact number. It depends on your data set, what might be more helpful. But you certainly don't want to have necessarily a data set with 100 different categories, or one with just 3. You're not really getting the information that you want if you go to something like that when you're working on a histogram. And they've got this listed in these different tables. And this is on page 79, where you have the rate of return for mutual funds. You want to make sure that you don't go from like 0 to 10 and then 10 to 20 or something like that. You have to have some kind of a necessary gap in between so that they don't overlap. So then when you see it happening here, it's between 8 and 8.99. Now, again, I don't love this because it has too many categories. There's a lot of different categories here. And so then when we look at this and we say, okay, there's no overlap, then when it asks the question, what is the width of the classes? The width is from the bottom of the first one to the bottom of the next one. So these would have a width of 1. We think bottom to bottom or top to top, that's the width of the class. Now, depending on what might happen here, I don't think I have. Oh, I do. If I go to this, oh, all right. So I just clicked on the link that's in the textbook, and I got a set of violent crimes for a certain country. It doesn't tell me. And what I'm going to show you here is how we can do this in the software that comes with the textbook, which is called StatCrunch. I just want to show you this so you can understand the possibilities here. If it's going to work. Come on. Did it just leave? Oh, I did not want it to leave. Oh, no, here it is. You try it. Let's just open an Excel and then we can copy it. All right. So it is helpful and positive for you to know how to do this using some software. It's not absolutely necessary, but it might be nice. Oops. There we go. So I'm going to graph this in a histogram just to see what it looks like. And as you can see here, I've got different numbers. I've got, could you close that door for me, please? Thanks. But when we say, what does this actually look like for a histogram? And we're starting at 0 and we have a width of 200. There's no rule that says it has to be a width of 200 exactly. It's nice that we can just pick nice numbers like this, but we could do, other things. And so then the shape of that histogram is going to change depending on what we pick. And so then if we say, well, I only want 6 categories, maybe this one, but then I could even change the starting point. I don't have to start exactly at 0. I could pick something else up here. And then again, the shape of the thing is just changing all over the place. So when we create a histogram, even though it's something that shows us relationships of what categories are large compared to the other ones and so on, to a certain extent it's artificial because we just decide where we're going to start, how big the different categories are, and there's no rule that says it has to be one way or the other. One thing that you might notice about a histogram is that the bars are connected. So we're not going to have like Wisconsin versus Illinois versus Minnesota where they're all separate. The bars will be connected, and this would be like 20 to 219, 220 to whatever it is, going up like that. So histograms, useful as they are, tend to be somewhat artificial because we're kind of imposing our will on the data, and the data is not really telling us what's necessarily going to happen. So then we have something else that we can make, and that is called a dot plot. What does the dot plot look like? It looks like this. And I'll squeeze it up here a little bit. And then I can print it maybe or just copy it. Open a new tab. There we go. So here's what a dot plot looks like. And as it turns out, this is more common in research these days compared to the histogram. Because when you have a computer, then you can make things happen easier. And so histograms are something you can do by hand, where a dot plot might take you some time, but if you have a computer, you just click, boom, there it is. And so then it's pretty obvious that the data itself is all represented in a dot plot. Whereas in a histogram, you don't necessarily see the different patterns in the data. So it's good for you to be able to do a dot plot. And I guess I'll erase this here. When we say, what does it require to have a dot plot? You need to have an evenly spaced horizontal scale. And this is definitely something that I'm going to want you to do for the project, is to have a data set and then to be able to look at the data based on the dot plot. And the two things that we get from a dot plot, which we don't necessarily get from a histogram, would be any gaps and any clusters. When we look at the data itself, we see that there is this definite gap here right below the 600. Here's 500. The top part of the 500s, there's a gap in that data. And a histogram would not pick that up, because a histogram can have any kind of a collection of data values. It could be here from here or here from there. It's most likely not going to have that gap right there. And you see how there's high amounts here, but there's also this high amount here, a high amount over here. Those things wouldn't necessarily, again, be in a histogram, because the size of the histogram bars doesn't necessarily reflect those particular places. Now, of course, this one way out here, pretty obvious. Something's happening there. And so we need to talk about that. That thing out there is called an outlier. Now, as it turns out, your textbook has a specific definition of outlier, which is mathematically used for a formula, kind of an equation that you put numbers in. The trouble is, different textbooks have different formulas. So it's like, how do I know what an outlier is? Well, it could be this or it could be that. Depends on who you talk to. So instead, I want you to understand what an outlier is, in my estimation, and that is a data value separated from the main data set. So that means it's more of a subjective thing. Here, not very subjective. Clearly, we've got one data value that's way out. But depending on the situation for the data that you have, you might have 3 or 4 outliers, or you might not have any. But what we're looking for is some kind of thing that seems to have an influence that makes it different from anybody else or anything else. So we look for those outliers, and we look to see those unusual events. If it's way out there, then that doesn't happen very often. Then we say there's something unusual happening, and we would maybe want to figure that out. What is happening that makes this so much different than anything else? If we're talking about crime rates, it might be that this is a very dense populated region of the country, and the others just are not. Who knows? Now, in addition to that, you need to understand the idea of skewness. This is on page 86 in the textbook, and you need to know how this particular thing works. We'll run into this on occasion, but this is something that, how can I say this? Just the definitions and the terms kind of go against your natural senses of how things work. But here are the 4 basic types of skewness. The first one is uniform. That means everything has pretty much an equal chance of happening. This would be the bell shape, which is very common. We'll talk a lot more about that in the future. But then we have the idea, what makes something skewed to the right versus one makes something skewed to the left. And when we say it's skewed to the right, that means the data is spread out at the higher levels or to the right. Skewness is where the data is spread. Same thing is true here. Skewed to the left, it looks like the middle is right here at 110 or 120. As we go to the right, it just tends to fall away, but as we go to the left, it's spread out this direction. So if the data is spread out here to the left, that means it's skewed to the left. And again, it's just something where knowing what that actually means helps you to be able to correctly describe the data. There are many data sets which are skewed to the right. There are some which are skewed to the left. There are also many which are more symmetric. And again, some of this is a judgment call. How symmetric is it? How skewed is it? There are various measures we could use, different formulas, but to a certain extent, we kind of look at it and see what's happening, see if we can understand it. We'll talk more about that down the road once we get there. All right, so those are the things I wanted to talk about today. And so then hopefully as you go through the homework set and the quiz, that if you have any question, you'll let me know. And they are due at the beginning of class tomorrow. So I'll see you then.